Swayam Prabha. Digital India. Educated India.
Right. So what is the while rule? So let's suppose you know about the loop body C. Okay. So it's a constructive proof. You make the proof of the small parts and build the proof for the entire thing. Okay. So you know about C that if you start with some set of states I and loop condition is true, then you guarantee to land within I. You cannot, you execute the loop. This is the inductive part. You start with I, you execute the loop, and you get back there. Okay? If that is the case, you can conclude that if you start with I, okay, loop can go as many times as it wants, and you land up with an I. Okay? But at the end, you have to exit the. When you exit, you get extra information that the condition has failed. Right? So you actually land up I and not F. Okay? So let me reiterate that there's a lot of things is packed inside this rule. So there's an I. Okay? And you know start from I, condition is true, then you land up in F. Okay? And you land up in I again. Okay? And so that means it guarantees if you start with I, loop will keep continue going to I. Okay? But now at the end we exit also. So the loop when finishes, then you will guarantee that the condition is not true and I is true because you always stay in I. So the question is how do you get I, and that's a really tricky business. Okay? So what happens is usually you have given a pre and post condition. Starts from here and finish here. Okay? And you say okay, prove it, this program is correct. But when somebody asks you this kind of question, they don't give you I. So you need to come up with I. So what will happen is what you do is that you guess an I. Okay? Guess an I, when in computer science, when you see the word guess, it's it's not arbitrary statement. It's a very peculiar statement, and over time you sort of get a sense of it. What do we mean by guess? Guess means you have to come up with an I. You're not just coin flip and come up with it. You give an intelligent answer to that question. It's like when in the exam I'm asking you to write an answer. That kind of setting is this. You can say that I can guess and write an answer. That's one choice you can make. But this is not what intended. In guess, whenever we in computer science we mean guess, what it means is human has to make an effort. So make an effort to make come up with I. Okay. So this is what the proof would look like in a full setting. Okay. You will come up with an I. Okay. And then what will you do? You basically you derive this. Okay. And then you will show that from the precondition implies the I, and also show that the thing which you learn here implies the post. And then from there, this weakening rule, you can derive this fact. Okay? So the thing is, you may actually prove something much stronger than actually asked. Okay? And then you weaken and then you show it actually that, this proof works. Okay? Right. Okay. So the finding I is a non-mechanical step. Everything else I have shown you before, is a mechanical process. You can algorithmically do it, because when I was doing this weakest pre and like require rule or assign rule, they're all mechanical rules. You can just apply them. But the finding I is a not a mechanical rule, and there is no algorithm of finding it. You have to come up with it. It's like, remember, first induction problems you solve in your high school, right? Induction hypothesis, you ask your teacher, how do I come up with induction hypothesis? They will never tell you there's no algorithm to it. They will always give you the example, and then they give you 10 examples, and somehow you get a confidence in your mind that I can do it when it comes to exam. But did you ask yourself, is it even possible in all possible settings? No, there is no algorithm. That's where mathematicians, that's coffee in, induction hypothesis out. Okay, that's what mathematicians do. Okay, and so far computers have not figured it out. The day they will, like, the world will come to end as we know it. Okay, okay, right. Okay, so let's look at our example. Okay, so thing is, so we have a formula given as starting point and the ending point. Okay, and we need, sorry, too many, sorry, too many things are happening here. Yeah, right. So the you have to find a formula at every gap which I have drawn. Okay, so you need to somehow prove this. Start with true. I want to prove r equals to 2z plus 1. Okay, so first I need to guess some invariant, right? So basically that invariant must be true at the start of the loop. Okay, and then when you finish, the invariant and the exit condition of the loop should imply the final property, right? That is what being said here. Okay, right? And then this part should also land up in while loop. So if you just go one more step back, you say the initial part, this part you execute should land up to the invariant, and the invariant, if you execute the invariant, it should hold, like as we have discussed earlier about the while loop. And if I can prove these two things, then I have a proof of the correctness of the entire program. Now what is my I here? Okay, what is my I? And just by looking at it, you cannot tell. Okay, as I said, you need to have human ingenuity to come up with I. So let me give you an I. This is my I. Okay, and this is what it's saying is, if you are at the loop head, this thing is always true. Okay, and finding this I is any verification method. Okay, so this is something which just soak in. Okay, if I give you this I, after this, when you have this I, everything is mechanical. Now you can run the algorithm, because all other steps are just mechanical, right? So if I give you I put this I in this formula, so I have two things to prove. True, r equals to 1, I equals to 1 implies I, so leads to I. So what I will do is, this is two assigned rules. I just substitute value of r and I, see if it leads to true. So you can just make it, let's just see it, it actually works. We have actually, this example has been shown to you earlier also. Okay, we have shown that these two things hold. Okay, right. So for this I need to prove that key, if I start with the invariant and the loop condition being true, I can always land at an I. So I have to show something find in the middle, but this can be found in the middle very easily just by applying the assign rule, right? If I execute the assign rule from the I can get there. Actually, this is a nice exercise. If you really not understanding it, you just do this part. You just take the I, which is this formula, and put I is equal to I plus 1. And maybe I can write on the board also. Okay, so what is my I is I is less than equal to 3. Okay, and r equals to I minus 1 z plus 1. So I have replacing with I to I plus 1. So I will just put I plus 1 everywhere. So I get I plus 1 less than equal to 3. Okay, r equals to, this becomes I star z plus 1. Okay, so this is the formula. So this becomes 2. Okay, right. So this is written in strict. This is the same thing as less than equal to. Okay, and you can check again. If you do r is equal to r plus z, it will land up there. It's so beautiful. Just do the, like, I would request you to do this mathematics by hand yourself. Once you see it working, you'll realize analyzing a straight line code and which has only branches is a solved problem. Okay, today there is a software called SMT solver. If you don't have a loop, you give it to them, they will tell you program is good and bad with definite guarantee. It's called bounded model checking. Okay, there's a software called CBMC. I think for C program, bounded model checking, C bounded model checking, and it can only deal with loop-free programs. So if you have a loop, what does it do? It doesn't say that I can't deal with it. It says how many times I should unroll it. It's unroll the loop that many times and then say, okay, more unrolling, I'll just ignore it. I don't know where I don't understand the loops. And then it will solve it, like as there are no loops. So without loops is a solved problem. It's a widely used in industry because the entire process is mechanical and you can give it to the computer and it can solve it. It takes a long time, it's a lot of work, but of course you can put thousands of computers on it. Okay? So loop is the problem. This is the one important message. Okay? Okay. So basically verification is finding invariants. If this statement is in your head right now, like I am successful. Okay? Rest if you didn't follow, doesn't matter. Okay? Right. Okay? Okay, so I have been giving you no.
When you were writing the whole book, sir, one part was above the
Right.
line, another was below. So could you please explain what?
The above things are already known to you. The things are you derive from the known things. Okay. So you small parts you prove derive. So reverse, when I'm reverse building is, so reverse thing is the things I need to prove. If I knew these two things, then I will have a proof. The argument can go both, like you can develop the argument in both directions, right? You get pieces, you can build things, and the things you want to build, okay, you you just simply say, okay, if I know somebody can help me proving these small two things. Yeah.
Sir, even in the previous one which we did now,
Yeah.
all of these were guess made, like guess.
I is the only guess. A rest is mechanical.
Rest is from the formula.
Rest is just mechanical process.
Like the while rule we used rest.
Yes, but for that I needed only I. I need to guess. Once you put I, everything is a mechanical. It's an algorithm.
But then how do we get the syntax? Like
Syn-
where
syn-
we put the I value?
You know that whenever you see while loop, it needs to be written like this. Like, but rules tell you, na?
Okay, so basically we need to have a brief understanding of the rules.
Excuse me?
We need to have we need to know the rules.
Yeah. These standard rules. Follow the standard structure. You know this I needs to be filled, and there is no algorithm for it. Okay. One more thing. If I is wrong, if you guess it wrong, this entire proof will fall apart. Somewhere something will not work. Okay, something will not match. Okay, right. So, right. Okay. So verification equals to finding invariants, and that important thing is like why you are here. Verification of analyzing smart contracts in Solidity. I mean, that's why you are here, right, in this room. Okay. So let me go over a Solidity contract and try to give you how would you reason about a Solidity contract. Okay. So this is a contract. Okay. And contract have variables. So what is the meaning of these variables, or where are they? When you put this contract in a blockchain, first the byte code, I mean, let's assume the source code, and let's not get too technical. Entire code gets copied into the blockchain. Okay, it's sitting in there. Then what it does, it additionally create all the variables of the contract, all the global variables inside the contract. Also, get some space. Okay, like you can remember the value of I, you can remember of wherever variable. So basically, you remember c.i. What is the value of c.i? Okay. If you upload the same contract again, then it will create another copy. So let's assume you uploaded a contract only one time. Okay, so there's a copy issue, but let's assume there's a one contract. Okay, for that. Okay. So once you can initialize the contract. Okay, so you can say constructor, when it runs, it sets I equals to 0. It can do anything. Okay, whatever you want it to do. Okay. Then what it does is you can have functions in the contract. Let me call it body, and there's a reason why I'm calling it body. Okay, and you can also increment I, do whatever you want, check I is less than 10 or require whatever. So the required semantics is that when require fails, you unroll back, you don't change. So for example, if you say I equals to I plus 1, I becomes 1. But let's suppose require fails afterwards, the change will not be committed on the blockchain. Blockchain will, like, locally it will be, miner will be running this code body, and it says at some point of time it will say, oh, my require has failed. It will say, okay, I'm not committing changes, I'm recording that this run has failed. Okay, right. Okay, and the important bit is, important bit, this body can be executed by any function. So if I am a Ethereum user, I can take any contract, any function in the contract, I can say run it. I have to pay for it. Okay, I can make it run. So that is the, but thing, what you can do is typically you check, like who has sent you, like in the contract you can write down only run if the require the user is equals to me, okay, some particular user, okay, otherwise it will just won't run. Okay, okay, so then so the properties are not any special function, it just happens to be another function. It has a one assert written in it. It also can be run any number of times. You can basically check I greater than or equal to 0 anytime. Okay, so let's suppose you have such a contract. Okay, it has assert written in it, and you want to check what it does. So the thing is, this implicitly there is a loop here. There is no loop written in here, and this is one thing you need to internalize. These functions can be run any number of times. So they are all in a giant loop. Okay, and any possible time there will be some invariant must be true all the time. Okay, let's check this contract is good for us or not. Okay, so you have a basically I think it's called 202 simple split dot sol. Let me see, it is the correct one. Right, this is the one. Okay, this is the program. I'm starting at 1, it doesn't matter. Okay, right, so let me run it, and it found some invariants. So it is saying that this is true about this contract always. So what did it learn? I is never less than 0, basically it's saying. Okay, so it's a complicated manner, and I is not of I is less than greater than or equal to 10. Okay, notice that why it is saying so. Okay, let me show you a small change in the code, and it will change its answer. If I check before, then does it change the answer? Oh, it actually forgets that. Very interesting. I didn't notice that. But anyways, the fact is there, but it did not derive it. Okay. Okay. So the thing is, what it does is that it doesn't have to learn about 10, because I am checking I is greater than or equal to 0. That's only is a relevant fact for me. So it will just other invariant. If it doesn't learn the fact related to 10, it's okay, because my property is about 0. I is greater than or equal to 0. Okay. Now, I have a question for you. If I do this, what will happen? Is this program correct or is it wrong?
Sir, I will keep on increasing.
Keep on increasing. Yeah, you can call as many times you want. So, excuse me? Louder. Only. Yes, so can you make it negative? No, it's an integer I8, integer of 8 bits. So what will happen?
So sign bit if 1.
Yeah, overflow. So how many calls later it will overflow? 127. Okay, let's see. Our algorithm does the job. One thing to note is taking a bit more time. It has to unroll, try to explore all possible times it has to execute. and oh, it found the counterexample. Well, I knew that it is going to do that. Okay, so it found 127 calls later, the sign flipped. Okay, so this thing can also find counterexamples. Okay, right. Okay, right. So so this is the core of it. So you have, let's look at 3. So this is our example, which I have been going over it again and again, and it's written as a. So the thing is we are using a Sol-C compiler, and there is an analyzer, which is called model checker, written inside it. Not very good one, I must add. And there are other tools out there which are nothing to do with Solidity toolchain. They just take the Solidity contract and analyze it. There are companies who are, you can buy those things. They work far better. But the one inside the Solidity, I managed to break it so many ways. Okay, so I was worried that I will be able to teach effectively. So if you play with it, you will find that a lot of things you will do wrong. It is not properly. It's not like, it's experimental mode still. Okay, so let's put it that way. So for example here, if I give this contract, it will not. It needs to find the loop invariant. It needs to find what is the invariant, what is true at the head of the loop. But it will not report it to you. It may be able to prove it, because it doesn't print anything happens inside the function. It only remembers reports only on the contract level. So so if you check this program 03, it succeeded. So it doesn't report anything because there is no global variable to report on. But I wrote the same program into a split form, which I have been talking about, 4th. Okay, so in this split form, so you can also open this program. Okay, and right. So to try to answer this question, try to run this and try to answer this question. Fourth question, the fourth file 04-quiz must be there. Did you find that file? Right? Just you want to go to the folder and click on it, it will open it. And try to answer these questions. So what is the largest bound, like I am bounding at 9, what can I keep increasing it, and what point it will give the error? Can you just play with it? And what will the largest value of z for which the contract is safe? Okay, so I'll just go around, and so now we will play with a sequence of examples, and you play with them, make minor changes, and see. Let's go around and see if somebody needs help. Okay, so I see many of you managed to do it. So, okay, so let me give the solution anyway. Okay, so so if I go to 64 here, it is supposed to give error. Let's see if it works. So if we give a counterexample, it is saying that if at 64, if z is 64, then what happens is z is being added 2 times. So 64 plus 64, 128, and it overflows. But if you do 63, it says safe, because 63 plus 63 is 126 plus 1, 127, it do not overflow. Okay? So okay, so the second part of the question is if I uncomment it, sorry. So it finds a bug. Okay, it says that this thing does not hold. The reason being, The reason being, it is checking all the time. This property function can be run all the time. So even just after construction, you can call it. And when you can call it initially this fact is not true. It is only true when you have you already had run loop body 2 times, right? And the third time you cannot run because it has a require on top. You cannot call loop body at all anymore. Then only you should check. Okay? So the check has to be put in place. So this is illustrating an idea that there are things in life needs to be checked only conditionally, often. Okay? Your parents will ask for, like, do you have a job when you graduated in college, not before. Okay? So you have to always check things against conditionally. Sorry. Yeah. So condition is, what condition is? I is greater than, let's say, 3 or something. No. Greater than equal to 3, let's say. Okay. One more thing I want to tell you, you can cheat here. Okay. Cheating means write false. You never check, you are always safe. Okay. Right. So this is like it is one big problem here. Right. If you give this thing in the hands of a programmers and say, okay, write asserts, and you need to tell me in what condition you check the assert, but the guy always writes false. He said, okay, I wrote thousands of lines of thousands of asserts, give me money, but everything is guarded with false and it's doing nothing. Okay? Very, very tricky business to turn this into an operational business model. If you hire a company to write asserts in your contracts, how do you know they have written a proper require? Okay, require means in what conditions you check. Okay? Very tricky business. But yeah, people are working on it. The problem is somewhat solvable. Basically, you try to figure out what conditions they are not checking. Okay, so yeah. Okay, right. So so this is this contract 5. Okay, so this is another example. So as I said earlier, how much time do I have? 15. 1 second. 11. Oh, I still half an hour. Okay, so okay. Right. So this is another program, eq.sol. Okay, 5th program in our list. And so what is happening? Is this program correct or not? Tell me. Just look at it, stare at it, and tell me it's correct or not. It's the 5th program in your directory. Okay. So what is the reason why it is correct? So what is the invariant? What the invariant will you write? I equals to R. Right. And I is less than 8 or 9, whatever. Yeah, it's less than 8. Yeah. Right. So I will show you this guy will have, I think, trouble proving this. Let's see. It is saying R plus 1 can potentially overflow. And look, it gave an answer, it's a weird answer. We have not seen this before. We saw when it said that something is wrong, it gave you a counterexample. But this time it did not give me a counterexample. It said might happen. Okay? And it proved the assertion. Assertion went through. The assertion we wrote I equals to R. For that it actually found the invariant. It knows I equals to R. Look at the invariant. If you read it carefully, it is saying I equals to R in a very complicated manner, but it is saying I equals to R. Okay? So that worked, but overflow business did not work. So this can happen. So to avoid overflow, it needed to learn that I is less than equal to 8. It did not learn that fact. So this is I said that there's no algorithm for invariance, right? There is this is like some sort of lack of better term, some kind of learning happens. It looks at the code and learns what invariance it needs to get. And I'm using learn in a very loose sense. It is being recorded. I didn't mean deep learning or whatever. That's okay. Okay. Right. So it learns the invariant, and sometimes it may not be learned the appropriate invariant, that needs to be learned. And at that time, and then it will try to look for the counterexample. And it could not find the counter. That's why it took some time. Neither it could find the counterexample, nor it learn the right invariant. Then it will only say this is called false positive. Okay, false positives means basically it is saying that there is something wrong, but it is not wrong. Right? And these kind of tools often given hands of the programmer in the industry. And if you go to conferences, and they always say too many false positives, doesn't work. Okay, and they don't want to use it because in a small program is like this, they will be like tens of thousands. And their manager will say, read each one of them and tell me why your program is correct. I say, I don't know program is correct. This tool is saying I doesn't know anything. So why am I supposed some idiot telling me I can't analyze your program? Why should I go about thinking about it again? Right? The guy is not good. Why am I being bothered? So there are software like Covarity. Okay, I should not name any specific software. Okay, so there are software out there which are being sold, being bought. They have false positive issue, and they report. They said something can potentially go wrong, and programmers don't like it. So the name of the game is today to build tool which reports minimum false positive, and that's where a lot of machine learning techniques, like you just look at the thing. Let's not report this. Okay, it's a low priority. Maybe things are wrong, but let it pass. Okay. So keeping the programmer happy is also an option. It's also an objective. Okay, so it gets murkier as you go along. However, if I'm being a bit clever about writing my requires, I can make it work. How do I do that? I can just simply say and r less than 8, and this will know it proves it. It doesn't change the meaning of the program. Program still has same meaning. What the r less than 8 did, it gave extra information to verifier. Here is an important fact, maybe you can use it. So as a programmer, you need to be aware of these analysis tools and their limitations. And then tell it, here is the extra information. Write programs in the same patterns again and again so that it can analyze. This trick is being extensively used by hardware developers. Intel and all those companies are building, chips, and they're writing programs. The chips are designed as a program, right? And they basically stick to very strict patterns. They don't like arbitrary programs, okay, such that subsequent analysis tools can understand what they are saying and then first produce good circuits on the chip, which are not hot, take less space, things like that. And also you can do good analysis. Okay, so right, so this is 5. Okay, 7 is a sort of your exercise. You can just go berserk on it. 06 is something, is not a verification thing. It's something I want to talk about. I have not, so whatever I have done so far, one thing may be disappointing to you, to some of you, is that I talked about smart contracts, but actually I'm just talking about how to find bugs in a program. It's nothing specific about the smart contract. So what are the issues in the smart contract and how can you check them? Okay, so this is one important class of bugs, okay, which smart contract writers often make those mistakes, and the tools are being built which can check these things. And unfortunately, I couldn't make it check this example on this particular tool, and I'm still working on it. So let me just show you the problem. Okay, so this is a sort of this is a deposit fund is a contract. Okay, and this you can see there's an attack contract. So there are two. One contract will attack another contract. Okay, and try to understand how this mistake happens. Okay, So bug I have written here is the bug, so you know where the mistake is. So let's try to understand. So what it does, this deposit funds basically maintains the balances, okay, for the various addresses. So everything is an address. You are an address in Ethereum, a smart contract is an address. For example, in Linux everything is a file. Here everything is an address. Every object is an address. So you are an address. So every address is assigned an amount of money associated with it. Okay? So what you can do, deposit. You can deposit the money. You can basically call this function. And when you call this function, there is an implicit variable called message. Okay? So you basically message arrives to the miner. Okay, in this contract called deposit. So message will have some values in it. So basically this is an implicit variable, it's not explicitly stated anywhere. So message dot sender send you this amount of money. Say okay, I have put a bound of 100 is such that there is no overflow reported. Okay, and then you add that value to the basically sender's value, whatever. Okay, इसके balance you add the 7 by 100. Okay, right. Withdraw. So if somebody calls you for withdrawal, you take the balance of the person. Okay, you need the send, like whoever is withdrawing, you check their address. Message.sender is their address. Okay, and then you read their balance. Okay, so when you get their balance, you check if it is greater than 0. If it is not greater than 0, you just not execute this. Okay. Then what you do, you basically withdrawing entire money. It's no amount here. So it withdraws everything. This is very simple code. Either you put some money or take entire money out. Okay. So what is this function doing? So what happens is when a message sender sends you, look, go ahead, take the money, withdraw the money. Well, I have recorded the money, I have reduced the amount of money. Where did the money go? I have to send back a message. Here is your money. How I give the money. Okay? So basically you give the money to another contract and they will have a function in which receive. You take the money. Okay? So that function is being called here. Okay? So basically what you are saying, you sender, you call that function, okay, which is called fallback or receive. It doesn't have a specific name. So it has a fixed name in a standard, but you don't have to give the name. It knows you are trying to send money. Okay. So you're saying sender call, basically whoever sent the message, they will call the basically unnamed function. Okay, this is the name of the function. It means call the default function which receives the money. Okay, and then what do you do? If the money does not go through, then you basically revert everything. Don't change anything. Okay, so basically, if sending the money fails, then you basically require it, and then it will be rolled back. Okay, and then you write to basically say message money has been sent, and then in its address you write 0. Okay, so what can then go wrong in this one? Okay, simple thing. So this attacker contract comes along and reads, this code is public. He reads the code, he says, this guy doesn't know what he's doing, so he writes this contract. Okay, so he says, well, I am going to, when I get allocated, I will pick up this deposit funds contract, and when I am being created, I will basically put my my address and put some money there. Okay, right. So what will happen is the attack works like this. Okay, read this code. You deposit some money. You deposit one unit of money, 1 Ether, and then you try to withdraw that money. Okay, that's it. That's the attack is. Okay, but there is a slight complication there. Okay, when you try to withdraw the money, when the deposit, the withdrawal will run in the victim, right? They will call your callback. So where is your callback? The callback is called this function, fallback. You call the function without name. Remember that? right? So in that, there you called a function, this function without a name. It means when name is not given, there's a default function to be called, and that function is called fallback. Okay, so you call the fallback function, and what it does, it calls a withdraw again. It is calling in the loop and it's taking money in again and again and again and again. Contractor keeps sending, victims keep sending the money. This is called reentrancy bug. This would not have happened if this line was written before. Because if you call re-entry, that this check will be made. The balance will be already zero, it will stop and exit. Right? The mistake was before you did not change your internal state and you inform the world that I am going to change my state. But that can be exploited. Okay? So there is a feature in this solver which basically can check reentrancy checks. It says that it does, but when I try to run it, it is not reporting this. If you give this contract to them, it will all say all fine. Okay, so I am not able to figure out why that is. Okay, but just to tell you that where the technology is, where the limitations, research opportunities is huge. So right now, if you are someone who can write this assert and requires, okay, for per contract, the rate goes in hundreds of thousands of dollars. Okay, to really fortify a contract. Okay, if you're a freelancer, you can do this and make a lot of money. Okay. So just yeah. So this is something. Okay. So the one thing I want to add here is that maybe try the next problem 7. Okay, so I will stop here and you work on the 7th problem, and then we will be around and help you. Okay, sure. Any other question, please ask. You can ask. Yeah.
So then when the line was below, what was happening that so that the balance was being exploited?
Yeah. So the thing is, so this is a callback. Basically, it's a callback, right? You calling external word function, okay, and you don't know what they're going to do, okay, when you wrote the contract. So they can call you back again. So they create a loop. You can keep, like they call you, you call them, they call you again, and then you can go in a loop. Okay. Now this loop can make you send money again and again. Okay. Because this is a money sending call. Look at this. It's called payable. It means you are sending money. Okay. Right.
So the attacker has that external function also that is asking for the
Attacker has this function, right? Fallback. And what is your question?
So like that was function which is sending the money, you told that it is connected to external system.
Yeah.
So
Right.
So the attacker will take advantage of the external function to.
You need to expose your functions to the world such that they can do something with it. If you block everything, then again, so the purpose of contract is to interact with the world. Okay, okay, that's the intent. Okay, if you block everything, as I said, the car that doesn't go anywhere is a safe car. Okay. Yeah. Okay. Right. So try the 7th problem. The question is in the middle, right? This is written as a Q. Oh, sorry, there's a mistake in your file, minimally. Okay. Okay. I saw Sarva's message. I said, okay, I'll take pictures. Okay, so the question is, there is a require written in basically you're playing checkers in this game, and then there's a statement which says how do you capture the enemy, okay, and if you run it as it is, it will sort of crash. The question is how do you strengthen this require condition such that you want to minimally reduce. You don't have to write, if you write false here, everything will become safe, right? So you want to reduce as little as possible.